All right, sorry about that. Hello, everyone. Welcome to the Graduate Student Community Seminar Series. Today we have a really exciting talk from Dr. Wesley Honeycutt. Before that, though, I want to introduce you to the GSC, some of our upcoming events. First of all, this is our leadership team for this semester. We have our co-chairs, a wonderful publicity team, treasurer, support, and of course, our faculty advisor, our mentor, Professor Farouk Mystery. Um, you can always feel free to reach out to any of us on the team, shown here. If you want to learn more or join the team, we would love for you to join us. And I'll get to contact information right here. So we have regular leadership team meetings Friday at 4 p.m. We're doing a hybrid meeting this year. So we meet both in the Burt team room in the engineering lab building and on Zoom. So we would love for everyone to join if you're able to. You can either send an email to Rachel Bennett or myself, and we'll send you the Zoom invite or make sure you know where the Burt team room is. And just for clarification, these meetings usually change time every semester based on when the most number of students is available to meet. This next one is really important. Please become a member of the GSC on Engage if you haven't already. This helps us secure funding so that we can still provide food for these seminar series and host other events to build a stronger community here at OU. So we'd also like to share the GSC LinkedIn page. We will be posting these seminar series on the LinkedIn page, invitations for them, and it helps us connect with current and past members to keep that community going. Same thing for Facebook and Instagram. If you're more comfortable on these sites, we also post there, still maintaining the strong community. And then I think one of the most exciting ones, these seminar series, we post past seminars on our YouTube channel. So if you miss any or if you want to go back and rewatch it, you can always go to our YouTube channel and see it there. And lastly, especially if you want to join the GSC leadership team, this is a picture of the Dave and Susan Burt team room. So it's available for all GSC members to use. It's in the engineering lab building. There's a few amenities there. We have couches, whiteboard, coffee pot, microwave. And it's a good spot for you to do some work if you need a place on campus that you don't have otherwise. So email myself or Rachel if you want access to this. And of course, please join the GSC leadership team and we'll get you set up. And then there should be a link in the chat already. Please fill out the seminar attendance. This makes sure we know who is here, but it also helps us maintain funding so we can continue providing lunches and hosting these events. All right. And then some very exciting news. Many of you already know about our food festival, International Food Festival, that we have 1 to 2 times a year. This is coming up again, March 14th. We're rebranding slightly. We're calling it a faculty, staff, and student mixer. So we're really trying to build community between students, faculty, and staff here in the college. But it's the same style of event. We welcome everyone to bring a dish from their home country, their hometown, or anything else. Share your culture, your favorite food with us, and have fun for a couple hours on March 14th. So this QR code will take you to an RSVP form. You can tell us if you're coming, if you're able to bring food or not, and get more information about the event. All right, and with that, I'm going to pass it over to Dr. Wesley Honeycutt for his talk today. Thank you very much.
It's Rodney. Going to start sharing my screen here and make sure I have the right desktop up. Okay, everyone should be able to see my slides. So, I am the illustrious Dr. Wesley T. Honeycutt. And my background, which you should be able to see on the slide now, is I have a background in a lot of things. I'm interested in sensors and making sense of how we sense the world. So these are words which I've taken from all of the papers that I could find without digging really hard on my hard drive. And I've created a word cloud, and you can see that a lot of the things that I do are sensor related or network related. But if you look closely and really dig into it, you can see a few things about what I sense. So I'm going to highlight these, and you will see that I don't necessarily sense just one thing. Sure, a lot of my stuff is on methane and CO2, but I'm also looking at bird strikes. I'm looking at ambient light. I'm looking at silhouettes, humidity, temperature. These are all different things that we can sense and try to make sense of as we analyze our world. So this is going to be an interactive talk, so heads up, if you are not comfortable talking with your mic, go ahead and put things in chat. So I have things set up so I can interact with you all there. So here in a second, I'm going to have you talk about what you sense, so have that on your mind. But let's give you a high-level definition of what sensing is. So a sensor is something which is capable of outputting signal and can describe part of our physical reality. There's a few things sometimes that aren't necessarily physical, but let's not get into that. A sensor can only detect what is present. So a sensor is able to tell you what is there or what is not there, or something you have told it to count. Similarly, sensors respond with a signal that we have to deal with. Sensors must be logged, modeled, analyzed, or some combination. And if you place a sensor somewhere that doesn't have this part, it's absolutely useless. If you detect something and don't know what to do with it, it's not really a sensor anymore because it's not intaking and describing physical reality. So, question time. I would like you guys to put in chat something that you sense. It can be something that you sense in your graduate student or undergraduate work, something that you sense in your daily life, just anything. Just put it in chat. Okay, great. We have Roshan says pressure. The smell of tacos, fantastic. Temperature, light, sound, stress. Roshan, that'll be interesting to think about what kind of stress you mean. This is great. Connor's brought in time. I'm not sure time is a physical reality thing, so that's a good representation of things that aren't necessarily physical. Siavash wants to detect happiness. I think that's a very good thing, and it will have some very special sensors you have to use for that. So this is great. So we're going to talk about these two, and feel free to put more in. But I want to give you an example of what sensors do to describe an environment. So let's talk about plants. I feel like we've all probably seen and heard the story of how plants generate energy. They use photosynthesis to take a photon of light and convert CO2 and water to glucose and oxygen as output. How do we describe this system? Well, we know that the light has to impact with some of the photosynthetic cells. There has to be water intake, and then there has to be CO2 intake and O2 outtake. This means that there is some relationship with the gas and the quantities of gas, which exchange with the stomata. So I don't know if you've seen close-up pictures of leaves. I took this back when I was in grad school. They're actually really nightmarish looking. They have all these little mouths called stomata, which are constantly breathing. So they exchange the gases with the environment, water goes through the roots, and light comes in. We can describe this system with sensing. So there's more than one tool that could do this. So there's humidity and water information, light, temperature, and pressure. These are all things which describe the system. If you're wondering why temperature and pressure are on there, that's because we're sensing gas. If you remember Chem 101, the amount of gas in the air is related to the gas properties. But there's more than one way to do this. So for humidity, you might use a rain gauge, a humistor, a conductivity sensor. These are all things which give you information about water. Similarly, light, There's all these different tools you can use to detect light. Temperature, do you use a thermocouple? Do you use a thermometer? Do you use a thermistor? Pressure, so on. All of these different things have different properties and ways that you interact with them, but there's more than one option to deal with it. So let's talk about sensors for computers, because I feel like this is what we're all used to. Most sensors work as a module for a computer. That means you can plug it in, and then the processing of the signal happens at the computer. And they can either be smart or dumb. Smart devices are things like your cell phone, where they have some ubiquitous capability, where they can have sensors on all the time. The human doesn't necessarily have to interact with them, and they can interact with other devices in the network. Or they could be simple. I say dumb here as the opposite of smart. If I have a sensor hooked up to an Arduino microcontroller below, it can log without any interaction. It just does its job. Both of these are valid methods. But you don't just have to use a computer. Not every sensor has to be electronic. So my background is chemistry. Whenever I think of a non-electronic sensor, I think of pH paper. If you haven't used it, it's a little strip of paper that you dip into a fluid and it changes color to tell you whether it's acidic or basic. That is a sensor that you can use. It's not repeatable for that same piece of paper, but it's still sensing the environment. But of course, it needs a logger and another sensor to record it and a special logger. We'll talk about this a little bit later. So I'm going to do a question now. So let's say I want to detect an earthquake. I would like somebody to tell me, interact with me via voice and tell me, how do you detect an earthquake? You can put stuff in chat too, but I'd love if you just shout something out.
Sound. Feeling the motion.
Vibrations.
Okay, great. I'm hearing sound, motion, vibration. I see seismology. These are all the information that you're getting, but how do you do it? How do you detect vibration? Oh, I see one sensor in the chat, a picture on the wall. Yeah, that will sense it and move. And if it's really bad, it'll scratch up your wall and record the information. Oh, pressure sensor. I'm seeing more things of how we actually do it. Well, I'm going to go through some examples and we can talk about all the different ways that it's possible to do this. Well, not all the different ways, but a few. Oh, fan back and forth, Tim's. We're getting a little bit more focused now. So this is the device that we've recently deployed on Mars for a Mars quake. Oh, feet, that's a good one. For a Mars quake. And this is a high-tech device that has all of these ground-penetrating sensors, heavily isolated, and it communicates with the outside going through a pipe. This is high-tech. This is probably what we'd be used to a modern seismometer. You could do this really cheap, too. I found an example of someone that's using a magnetometer and a stick on a magnet to detect vibration or record it with an Arduino. Very cheap. Old-fashioned stuff used a pen and paper to record a weight moving and draw a line. Even older than that is a vase that Han Chinese invented, I can't remember what century, where these little dragons have a ball in their mouth that when there's a vibration, drops the ball into the toad's mouth, which makes a noise. You can tell the direction of the earthquake from that. And then, of course, people. The human inner ear can feel these motions. And I mean, I see some of this in chat with like feet and vibrations and picture on the wall. These are all things that we can sense. Humans are sensors too. Here's where I got these photos. So let's talk about humans as sensors. We're pretty good at it, actually. If you send a human out to go find a bug, I've gotten really good at finding bugs in the garden because we're built for this. But we're not always great at quantifying. We can detect complex things like patterns, but this can be a problem. So simple detection is often driven by evolutionary imperatives, which means, I don't expect you to answer this, But can you tell me what percent gray that is just by looking at it in an isolated context? I doubt it, and I bet you'd just be guessing. We're not great at quantifying how gray something is because we didn't have an evolutionary pressure to do so. On the other hand, we can detect patterns that aren't there. How many sticks does this trident have? Does it have 2 or 3? Well, our eyes see these patterns, which we are, hardwired to detect that may not actually be there. We have to be careful to make sure we are actually seeing what is useful. So we've talked about humans as sensors. Let's go back a little bit to how computers are sensors. So let's go over what analog and digital are. This is going to be a very short explanation. Analog, well, first, digital is a number which is either 0 or 1. It's either low or high, off or on. That means it's quantized. So if we draw a trace of that, it is always going to be either on or off with absolutely nothing in between. On the other hand, an analog trace is any number between 0 and 1, or low and high, or off and on, whatever you want to say. It is a percentage on. That means we can have a much more complex data trace. Most sensors that we interact with at the very base level are analog, because most of the processes which underlie sensing are analog responses. But our data processing doesn't always handle that well. We have to quantize our information. So how do we do that? This is going to have a question here in a minute, and I'm going to have people shout out. So here is a analog trace. It's a sine wave going from low to high, and 100% of the signal is up here. How do I know when it's high and when it's low? I don't know. Let's set an arbitrary threshold. I'm going to say that the signal is either high or low at some sort of 10%, 90%. Because if I just said it's only high whenever it's 100%, for a sine wave, that's only going to be a single point in theory. So now comes the question, if we were to convert this from the analog signal to a digital signal, which one of these points at the bottom, A, B, C, or D, do you think the analog signal goes high? So A, you think it starts at the beginning. B, it starts whenever it crosses the 90%. C, whenever it hits 100%. D, whenever it hits the 90% again, completing the loop. So I see one in chat. Shout out or put it in chat what you think the answer is. Okay, I see some B and I see some D. B and D, interesting. It depends on the system setup. Yeah, that's possible. Okay, well, let's take a look at this. So if we have to tell it to trigger and threshold, then it has to have some sort of lower threshold. Ah, there we go, Jet. So here, I have set up this system so that it triggers at B. So once it hit 90%, it's high, and it stays high until it goes low. So rather than B and then down at D, it's always high until it's not, whenever it crosses that 10% threshold. I have no idea why that letter N is in there. I need to fix that. So let's talk about the shape of the signal, because once we start changing these and making an analog, things get a little weird sometimes. So in the real world, we don't actually have a completely digital signal. Things go from low to high and drift down a little bit. In this case, this is a capacitor charging up and discharging. So we have to characterize the signal, which is imperfect, based on the rise time, the fall time, and the amount it tilts. So this is a representation where we can describe the quality of the signal, which we are converting, whenever we assume that this is not a perfect conversion. Additionally, rather than try to account for how wide the signal is at the bottom or how wide the signal is at the top of this digital signal. We do it at the middle. We take the average and say full width at half max. So whenever we characterize the quality of a device and we're looking at things like response and signals, we have to use some technique to quantify. Well, this all brings in the concept of time. So let's think a little bit about actually measuring. How fast do you really need to measure? And can you do it? So whenever you describe a system, you have to consider how often you need to sample to answer that question, potential future questions, and whether you can actually do it. There's a lot of ways to do this because if we were to take in signals all the time for everything all at once, it would just be outrageous and it would be too much information and not actually useful. But if we don't do it right, it can kind of mess things up. So I've made this little example of the total stock market index for the past 110 months. And I've used different methods of doing a running average or a windowed average to sample these data. So the running average takes the last X number of points, either 5 or 10 in this example, and averages everything that came before. Whereas the windowed method says at set periods of time, I am only going to take this sample, and it's going to be an average of all of the points previously, 5 or 10. This is generally how sensors work whenever the humans interact with them. So if you have a device that just has a number that pops up every minute, say, I'm just rattling off, I think the thermometer in our house that controls the temperature updates the display every 10 seconds, I think. That means that it's taking however often it's measuring and averaging that and displaying the average at the end of those 10 seconds. This has ramifications. For windowed methods, low frequency sampling, you can have sustained regions of error. In this very obvious spot, it runs high when maybe it shouldn't. Whereas a running average will always be either under or over predicting based on the previous points unless you have a perfectly flat line. So the method that you choose to sequence time and control how you're observing it will change what you're actually observing. So this brings us to a topic of how do we actually characterize how good this is? Well, for a generic sensor, we are trying to find truth. But finding truth, we don't know if we actually hit it or not. So we have a distribution of responses. In this case, it's a normal distribution around sub-average. And we want to say that the trueness of the sensor, how good it is how far away the average is from truth. A perfect sensor, the average is at truth. So how do we characterize this? Well, we can use something like accuracy to tell how far away the entire distribution is away from truth. Sometimes this is done at like a few standard deviations or away or at full width at hat max. We'll discuss a little bit about that in a second. But if you haven't seen this drawing before, we are shooting at a target and we're around the target, but it's not really well focused. We're not trying to describe how clumped this is. We're trying to describe how close to truth it is. Precision is the opposite. We want to describe how wide our normal distribution is. So this is how clustered the shots are in our example. This isn't necessarily how perfect or how true the shots are, but how close they are together. We need both of these. Because whenever we describe a system, we have to consider the error. So there's two types of error we'll talk about with a little bit more specificity in a moment. Systematic error is there is something built into the system that is predictable that will always be wrong. Random error is something that we can't control and just pops up. These come out as some sort of noise. So these are some very ugly data from my PhD work, where I'm looking at two different types of sensors which measure the exact same thing. On the left, we have the response in terms of, I believe that's 1 over volts. And this is measuring methane over a period of 60 hours. The sensor on the top has both systematic and random noise, whereas the one on the bottom mostly has systematic noise. So the systematic error in this case is the broadening around what should be an average or a very perfect line. Whereas on the top, you see those drifts away from the mean. Those are shifts actually due to temperature sensitivity or humidity sensitivity for that particular instrument. It has multiple types of noise. So previously, we were looking at the normal distribution. Whenever we plot these, we can also get normal distributions and collect data on it. And I don't want to go too far into detail on this because it's ugly and I try not to think too much about my PhD work. But this is just a note that we are having a distribution around the mean to describe the noise of the system and quantify the error. So how do you know if you're actually looking at what you think you're looking at? And how do you know that you're numerically able to quantify it? Well, let's say we have some measurement. It has the distribution, and this is what our blank measures. So in this example, you can imagine pure water. Pure water measures like this, but then we take a measurement for salt water. If we have our peak over here, we have detected the peak. That's because we are defining the detection by a limit of 3 standard deviations away from the mean. And we can say that we quantify it if this is 10 standard deviations away from the mean. These numbers aren't always exact. Different people use different methods for how they separate this, but you need to have a strict method because there are logical things you need to consider. For the 3 standard deviation, you can feel confident that you detected something as opposed to detecting nothing accidentally if there is a 50% chance to have a false negative. That means if your response was somewhere in there, the area of that region under the 2 curves is 50%, equal to the area between the curve and the limit of detection mean. And there is only a 1% chance of false positive. Whenever you have detected something, you need to be darn sure that you've actually detected something. If you have a false negative, oh well, you can say it's a blank and it's an accident. If you say you detected something and you didn't really detect something, you need to minimize that chance. So 3 standard deviations makes that chance only 1%. On the other hand, the limit of quantification over here is completely separate. It is completely removed from both the measurement blank and the limit of detection. If there is another peak out there, you are absolutely sure to 10 standard deviations that it is separate from blank. You have detected it and it's separate, so you can put a number to it. If I was to take the limit of detection and try to put a number to it, I couldn't be that confident in how much I've quantified because there's a 50% chance that I'm wrong. So this is describing how sensitive and specific your setup needs to be. So consider this is a separation based on 3 standard deviations of A and B. If we were to measure one and it's a positive sample, there's a chance that could be either a true negative, a true positive, and we want these to be maximized. And there's a chance that it's a false negative and a false positive. Here, this is separated so you can kind of visualize what it means for the 50%. We call this limit where we are truly into the true positive as the limit of specificity. The sensor is specific for what you are trying to detect. On the other hand, right here, whenever we first start to detect the true positive, is the sensitivity limit. We say that sensors need to be both sensitive and specific. That means they need to detect very early on the true positive, but also be specific so it's completely separated. A good sensor would have a true negative and true positive very far apart, but that's not always the case. So let's do an example, and I'm going to have you, it feels like this is a chat room, so we'll answer this in chat. So I've got these data, which I pulled from some paper that I haven't completely read because I liked the graph, because I want to show you how do you know that you have one versus the other. So say you have a mixture of these two components. There's a mixture of orange and blue, whatever they are. If your sensor has a window that can only measure that wide, as we see on the screen, where do you measure if you want to know if you have blue? So can you put a number in chat for where you would put your sensor to know if you measured blue? All right, I'm seeing 2013. 2013. All right, we got a couple of 2013s. Oh, we've got a 2011. Okay. Or sorry, 2111. So these are both correct. However, if I was to choose one, I would choose 2013. The reason I would do this is because there is a wide separation between the peaks at 2038, 1996, and the 2013 that we're looking for. It would be sensitive and selective. So same question, what do we do if we want to detect orange? Pop it in chat, what number you think. We got a 2093. We got a 2138. You got another 2093. Okay. Well, these are both good answers. It's a matter of what you think is most useful. If your device is truly sensitive in that window, I would probably go with 2093 personally, because that is separated enough from the peak at 2111 that it could distinguish it, and there's a large difference in the response between blue and orange. Okay, now the hard one. What if you need a sensor that measures both blue and orange? Put in chat where you would put that. All right, so Claire says 2011 or 1996. Okay. And I see two sensors at 2013 and 2093 from Connor. Oh, Connor, you're breaking the rules. You only get one sensor, one shot. Where do you put it? The sensor, this little red box, cost $1 million. You only have $1 million for this red box, so you only can put it once. So I see 2230 and 2038. Okay, there's a lot of responses here. There's not a great answer for this. This is really hard. This depends on what you value. I would actually do none of the numbers, and I would go between 2018 and or 2118 and 2111, because there the peak in the blue has a shoulder, whereas the orange is a single peak. And that means if I see a response with a single peak, it's orange. But if I see a response with two peaks, it's blue. So you can be a little bit clever in how you do this so you can get more information. Well, thank you all for responding in the chat. I'm glad you guys are responsive. Yeah, I'm sneaky, I know. So let's talk about sensitivity. There is we need to report sensitivity in a way which is very meaningful. We need to be exact. And you may have seen this before, significant figures. This is the number of digits from the left side that are not zero, unless there is a decimal point, in which case you measure the entirety of everything from the right. So this is hard to describe over words, so I'm going to put in some color. If you look at this and see these numbers, this is how much you can believe. If you see 420, you can only be confident that the 42 or the 420 part, not the ones part, is true data. If we look down at the 10,000 in that first example, we only know that one is good. The rest of the zeros, we have no idea. Whereas we have a line over the bottom 10,000 that says we know down to that number. This is important because we need to know how precise our sensor is. A good sensor will report somewhere, if it's worth its salt at all, plus or minus how far around a mean value it should be. So let's take an example. Let's say I need to measure the size of this shipping container. And also, this is a note for myself that I need to go clean up my sensors. Say I need to measure this shipping container. We know that length, width, and height describes the volume. Great. That's how big the shipping container is. So if I tell you that the size of the shipping container in these dimensions are these numbers, we can do length, width, and height and say that's the volume. Wrong. That's because we know that the way we measured it, in this case, a class 2 tape measure has some error to it. It's plus or minus 2.3 millimeters. Okay, Wes. Well, we'll just tack that on and call it good. It's 3.8 or 38.27 times, or with plus or minus 2.3 millimeters. Wrong. That's because uncertainty propagates as we change the value. So each one of those measurements has that uncertainty. Math, I'm sorry, if you're scared of math, cover your eyes. We can describe this uncertainty as by multiplying the volume times the sum of squared variances to describe the total squared variance of the system. So for this example, I did all this with the volume that we had before, multiply it together, and we actually get that what we should be reporting, the volume is 38.27 plus or minus 0.05 meters cubed. That's a pretty big difference. That's 5 centimeters as opposed to 2.3 millimeters. This stuff adds up because as we start combining the information, we get more and more complex and it compounds. Error propagates, so we need to be aware of it. And this matters. So here's an example from data sheets that I pulled, where the electrical characteristics of a 555 device. Don't need to know anything about it. What I want you to look at is that the device should have 1.33 volts, and anywhere between 0.95 and 0.65 will be an appropriate threshold voltage. But the absolute maximum ratings say that it can go from negative 0.3 volts to 18 volts. So if I have a sensor that's measuring voltage elsewhere, and I'm saying, well, I'm putting in 1.3 volts plus or minus 2 volts, that will destroy this device because I have no way of knowing if that's going down below the minimum. Even though the voltage maximum is 18 volts, way higher, if it goes below the minimum, you'll destroy the circuit. So it matters what the precision is to how you design something else. So I'm going to shift gears for a minute and let's talk about space. So let's say I have some sort of information which is arranged like this orange sun gradient at the center of the screen. Where do I want to measure it? Well, That depends. If I want to know the maximum, the absolute top of the line, how much is going on in that spot, I need to measure at 0.1. Well, what about 2 and 3? Maybe the purpose of our sensor system is to measure whether we've even detected it. So in that case, putting it at 1 may not be necessary. Putting it at 3 may be appropriate. Now, something that comes up with me is imagine that this is methane. You can't put most sensors inside of a methane plume that's emitting from a source because it's electronic and it'll explode, and that costs money, and we don't want to spend more money. So putting a sensor at 3 is often a lot better than putting a sensor at 1. But what if you still need to know some information about how strong that emission is? Maybe you don't need to be just on the edge. Maybe you need an information about how strong it is, so you put a sensor at 2. If you have a model which describes how things connect between 1 and 3, you can put a sensor at 2 and get better data than you would get at 1 or 3 with that model built in. So remember whenever I said earlier on, or early in the talk, that sensors depend on the logging or the model or the analysis? That's because a good model can improve the quality of your sensing. It needs something connected to it. Spatial issues have more problems. So let's take a look at something called the modifiable area unit problem. So here is just a map that I'm making for something else, which has all the ecoregions for Texas and Oklahoma. And let's say I want to put an arbitrary grid of sensors over this. Well, great. So do I define the grid by sensing at the intersection of the line or sensing at the very center of the box? In other words, what if I shift over my grid by half in each direction? Well, it actually changes what I see. So if I take these two examples, for the first grid, I see a big majority of Edwards Plateau in the black box. But if I sample things with the red box, then I see a majority of Edwards Plateau, but a big chunk of Chihuahuan Desert and high plains. If you're not aware of it, this is how politics works. So politicians will arrange the maps for voting districts based on ways to still have a majority, but have a minority they don't want controlling the message as a minority in that box. They would choose the red quadrant instead of the black one because they would still win that district as an Edwards Plateau. So the where we put our points matters, and how we set up our system can actually change the data. Let's talk about precision a little. So here is a Google Map image of the stadium at OU, and I've put the pin right in the center, and I've said, hey, Google, what's this GPS point? And it spits this out. Great. Not great. Let's just take a look at the 0.9 or the -97 number and break it down. So let's think about what each digit actually means. So earlier we were talking about precision as a way of describing a system with error. Well, this error in this case describes what we're actually reporting. So the negative here tells us whether we're in the east or west hemisphere. In this case, we're in the west hemisphere. If there was a hundreds digit, we know that we're working with longitude. Great. This tens digit will give us roughly the continent that we're on. So it's 100 kilometer or 1,000 kilometer accuracy. 7 will tell us what country we're in. 4, which large city we're in, or the tens digit, excuse me. The hundreds digit, which town we're in. I can't even go that low while I'm talking. We get smaller and smaller down to the individual parcel of land. Tell which person you're looking at versus another person standing next to them. Down here, we're hitting the limit of what the GPS can actually do. Your phones can't really do that quality of GPS on their own. Even smaller. And down here, we're getting down to 110 microns with this many digits. But it keeps going. Those numbers are useless. So remember, whenever you're looking at precision, you don't just report everything because the computer spits it out. You have to report something that's meaningful. Okay, shifting topics again. Let's talk about how we actually collect and store the data. So we're going to go back to the example that we had for seismic issues. And we had all these different tools to do it. How do they actually collect the data and report it? This is very important. So in the Mars size instrument, it has a wire which transmits the data to a computer, which sends it in radio reports every, I think, 9 minutes. This urn has bells where the little bead drops into a toad and it makes a noise. And then the bead stays there until someone goes and, if you're the unlucky guy that has to go put the bead from the toad back in the dragon. This uses an Arduino, which has a small amount of logging, but then it'll have to be hooked up to a computer later on to extract that data. These examples, the ear assumes someone has a notebook, but this old-fashioned seismograph is literally a pen and paper. All of these things have to store the data in a temporary buffer. We often call this a ring buffer. So seismometers have actual rings. So this is a classic type seismometer, which has the ink pen writing on a piece of paper or on a drum, in this case, in a circle. So each one of these stripes is one long line on the drum. And it's storing all of that information on the drum so someone can come back and look at it later. This is a buffer where someone can get the data and then erase or change the drum to get more information. If we do this for a computer, this has, we still use the term ring buffer. So this is more stuff from my PhD. You don't need to look at all of this. I want you to look at this little box down here. These are the sensors that I had on this particular piece of equipment. They report information to the processing unit, which reports information to the cloud. Each one of those arrow steps can't just report constantly. This is sending data through a cellular network. And if I have that cell phone on all the time, sending data back and forth constantly, I'd run up a huge bill. I can't do that. So instead, I have this ring buffer. And if you'll see on the diagram on the side, the sensor data interacts with the processor, which stores information in the ring, which stores it to an SD card, and eventually it dumps everything to the cloud. We can also look at this as a programming challenge. So here's simple code to show you a ring buffer. So here I've just done Python. If you don't know Python, don't worry about it. This is just saying print the numbers until you have 10 of them, then print it out, and then dump everything to the terminal. And whenever we have the outputs here, we have these numbers output as strings, but this actually impacts the reporting. So if I told this information to do buffers of 5, it would report more frequently, but I would not necessarily extract the same information from that chunk as I would otherwise. Remember the averaging? If I was to average these, if I'm averaging between 0 and 4 and then 5 to 9, the number is different. So your buffer and how you design it will change how you interpret the data. So this is to summarize, and there will be a test question after this. Not kidding. I want you all to talk for this. I'm going to call on you. So whenever you analyze it, you need to go through all of this to describe your system and understand it to make sure you have appropriate sensing information. Because it's not just about the sensors. It's not just about the logging, and it's not just about the analysis. You have to do all of it, and it has to be useful and germane. So, test question. I want you to summarize this experiment. So I have a couple of aluminum coupons of an unknown aluminum alloy. Hopefully there's somebody with aerospace or mechanical engineering in here that has heard the term alloy or coupons before. I have some machine. This is a DMA to get data on the tensile strength of this material. It's hooked up to a computer and it's pumped out these data on elasticity for the alloy. These are measured elasticity values for the cast aluminum alloy. How would you use the data to describe this alloy? So, would anyone brave like to try this? Otherwise, I'm going to call on somebody. And if I know you, I'm more likely to call on you. Heads up. Oh, I see something in chat. So Jason must not want to talk. I want you to talk and describe this entirely. Oh,
The
Jason.
the data that you're getting from the sample. So what I'm seeing as I would just describe this alloy as having elasticity of 10,000 KSI, and just from your sampling, the information you give me, that's just how I would describe it.
Thank you. Thank you for being brave and jumping out here. And we're going to talk about this here in a second. And I want everyone to think in their head, how would you have described it? Because we're going to go over everything that we should have been looking at. So, how did you do? Is the sensor appropriate for this task? This is a device which is made to do this. It's appropriate. We're good. And we're going to assume that the computer is logging faithfully and that it has very little noise. I'm pointing at the little ferrite bead, which says there's probably not much electronic noise interfering with the data. So it's probably pretty good. But what about the rest? This depends entirely on how you frame the problem first. So let's say we're building a bridge. If you're building a bridge, do you need the minimum value, like Jason reported? Do you need the average value? Do you need the maximum value? It depends on what you need. Your sensor system and the way you interpret it depends entirely on your problem, because people can get hurt. This is the Tacoma Bridge. This famously had vibration issues in the wind because people didn't include wind information in the bridge design, and it failed. So, did you respond with something that said, this is just the mean? Because that may not be appropriate. There is some variability. So Jason, thank you for being brave. You did a minimum, but I wouldn't say that's good enough. I would like you in the future to say, this is the minimum with this variability. Or say something like, to avoid failure, we need to be within this number of standard deviations. So you went with the bare minimum, which is great instinct. Awesome. But there's actually criteria for this, which you may or may not be aware of. That's fine. For saying you want things in the 5th percentile, or a way to know and quantify to say that that will avoid failure. Because maybe just saying the lowest goes too low. Is that what you're framing for your problem? I don't know. So I don't want everyone to respond what they said. I want you to think about it in your head what you responded. Because, we don't know if it's spatially or temporally meaningful because we didn't describe that. So we're going to ignore that for the moment. But I want people to think about in their head what they responded. Because engineers don't do well with this task. This is from a study where people they asked engineers of different skill levels to describe a system exactly like I just did. Same problem wording and everything. The blue ones in this red box, so 6 of the responses had everything to describe it in a way that wouldn't kill people. But a lot of them didn't really think much about variability. Some of them just said, oh, the mean is good enough. And they're these red boxes. These weren't new engineers. They've been doing this for like one person up to 4 years. They would be graduating and they would be doing this in industry or in the real world at some other capacity. When you report this, you must report variability. You must understand what it means. And this all depends on how you have framed your problem. So this is the wrap up. This is what I want you to take away. I'll come back to this in a second because we're not going to be done, but I'm putting up my Let's Chat. So if you want to contact me or talk with me more, you can send me an email, honeycutt@ou.edu, or go to my website for more of my detailed information. This QR code takes you to the website. So let's go back to the wrap up. I am going to call on people that people I know first. That way it's a little less scary for everyone. So let's go back to something that you brought up in the chat for something that you measured, that very first thing. So Sivash, I know you. So I'm going to ask you to tell me about what you sense. Previously, you said you sense happiness. Can you describe that with a little bit more detail? Oh, I think Siavash had to drop off. Too bad. Who's here? Oh, Saramia. I haven't seen anything in here. Saramia, what do you sense? And can you describe it? No one wants to jump up. Does anyone else want to try? Bring up something?
I ate all the tacos, so I don't smell them anymore.
You ate all the tacos, so you don't smell them anymore. Fantastic. Let's roll with this. So, you have a well-framed problem. You smell tacos. Where did you smell them from?
The food tray I had in my lap,
How far away is that?
about a foot.
About a foot? So you're right there. You're
Yep.
definitely getting the intense taco smell.
Yep.
So do you think you would smell that elsewhere? If you were out in the hallway, would you come into your lab for the taco smell?
Yeah, it's just the one tray, so you'd have to be inside the lab, the office room.
Oh, okay. So if you know you have to be that close, do you think you could describe a model which would explain that based on your sensor placement?
Yes.
I think you could.
Yeah.
I think it would be a simple distribution. What else would you need to describe that, though?
Atmospheric information or air current information, the size of the door if you want to try and put your sensor in the hallway, convective motion in the office, density of smell particles.
That's great.
Yeah.
Yeah, you're describing a whole system which is based on how you framed the problem originally. And then you're adding in things that you also need to describe. So thank you for speaking up.
Yep.
And hopefully others can think about this in a little bit more detail. Think about what your topic is. What do you sense? So with that, I think I'm going to wrap up and stop sharing my screen and we can chit chat a little bit more. I'll be here for a while. So thank you all for coming today.
Yep. Thanks for having us talk.
Yeah, thank you very much. All right, thank you very much. It was really interesting. So like you said, we'll stay for chit chat or questions if anyone has anything to add or ask.
Thank you very much. I appreciate it too.
Yeah, I hope you all got something out of it.
Definitely.
So Rodney, as someone in the song lab, is this something
Yes,
below your pay grade or above your pay grade, or what do you think?
definitely not below. I think it's interesting. I really the slide where you compare like the moving average and discrete time samples was interesting because we have Of course, you know, we measure like air temperature, solid surface temperature. Um, but a big thing we're concerned about is like the rate of change of air temperature, stuff like that. Um, and also in the controls, the generic filter in those is just an exponential moving average. So we definitely see that's always either under predicting or over predicting the true value.
And it always will be. I mean, that's just par for the course. So,
Right.
you know, if you can characterize your sensors well and you can characterize your function well, then you can say, we know it's only good to this value. So you should describe it like that. It'll make your results stronger.
Right. Well, maybe to get our chit chat or question started, do you have any other considerations you take when you're concerned with more like the rate of change of a measurement versus the measurement itself?
So for rate of change, I tend to avoid thinking about it straight away. I try to focus on what my capabilities are of the sensor itself and of the logging equipment and base it on that, because often for small sensors and very few sensors, you can have a large density of information. So, you know, if you sample every 10 hertz, you know, that's a lot of data if you've got a million sensors. But if you have two sensors, it's very manageable. So you do the best possible there and then scale it down to match with everything else. And then there's other considerations where your sampling regime and your discrete time periods should be appropriate and germane for what you're measuring. That means that if you're measuring temperature, you know, it's easier to talk about this temperature outside. Your temperature measurement should somehow be appropriate for the length of day. So as that changes, you don't want to introduce more error than you have to by the shifting length of the day.
Yeah. Yeah. Yeah, something we ran into like with the smart thermostats like Ecobee or Nest. If you want to use data from those to input into your own models or whatever you want to use it for. There's the problem if they put in their own smoothing filtering algorithms, but also they only update once every 30 seconds to 1 minute.
Yeah, and a lot of those things don't even tell you what kind of smoothing they have, because there's much more exotic methods than the stuff I showed today. I've run into some weird ones, like one where it's just a single stack overflow post. There's not a paper on it that everyone cites. And it's very strange. It's a cool smoothing algorithm, but it's weird.
That's cool.
So Swapnil and Babak, I don't think you guys introduced yourselves. Do you want to say hi if you're here? Tell me who y'all are.
Hi, I'm Swapnil. I am a PhD candidate here in the School of Aerospace and Mechanical Engineering. I work with Dr. Jutesh Garg, and my work is mainly with polymer composites, developing thermally conductive composites, and I'm also working on 3D printing of those composites. And I really like your talk, though my work does not deal with a lot of sensors, but it was uh, very interesting to learn different ideas.
I'm glad you like it. I bet your work deals with more sensors than you really think about. I mean, if you use a 3D printer, that's all sensors.
Yeah,
That's what's
yeah, that's true. From
yeah.
what I meant was uh, like I don't directly have to put in sensors in my work that I'm doing right now because my work is, since it's mainly to do with materials, like fabricating materials. So that's what I meant.
Yeah, I know what you meant, but I also wanted to be like,
Yeah, that's true. The 3D printers, yeah, they do have a lot of sensors on them.
So whenever you have to print these like metamaterials or something like that, where you have a novel polymer, you know, the quality of your object that you're doing testing on depends
Mm-hmm.
entirely on the sensor quality of that 3D printer, which
Right.
means that if you have an uncertainty in your 3D printer, you have to build that in to the quality of your data and say, well, we only know it within this value.
Right. Yeah, that's right. Yeah, I mean, I just started using the printer, and I think, yeah, like you said, like I think even when we design parts in, let's say, SolidWorks or something, that might have its own errors, and then when you're putting it into the printer, the printing itself has its own errors
Mhm.
depending on its sensors.
Yeah, I have a printer in the back here, and I remember having to deal with error in shrinkage, where I had well characterized X and Y dimension shrinkage, but I didn't really understand the Z dimension shrinkage, which means I had a lot more separation than I should have otherwise. So I had more parts failing. So I had to go back and recharacterize and kind of build that into some of my settings.
Oh, right. Yeah. Yeah, once again, thank you so much for such a wonderful presentation.
It's beautifully done, Wes. The way you got people involved, chit-chatting, stuff like that was superb. But I think it probably scared some people.